think let's start. Okay. Hello once more time. Glad to hear you. Let's continue our work, the lecture number 3. What did we discuss in previous time? In previous time, first of all, on the first lecture, we were speaking about the basic physical values, about what does it mean voltage, current, resistance, what does it mean source and consumer. We discussed the main elements of mathematical model, that we have some sources, some consumers, consumers as the resistors, sources as voltage source and current source, two ideal different cases. After that, we were speaking a little bit about topology of electrical circuits, that we have such called branch, such called node, and mesh as a closed loop inside this circle. It was the first lecture, and the second lecture was about, first of all, equivalent transformation, to simplify the view of our circle. If we have resistances as passive elements, or resistances plus sources and as active and passive elements, we could simplify it for the same current through the elements they call series, and we could simplify them using formula for series connection, like here. Then also, if we have sources, voltage sources, also in series, we could connect them the same as resistances, just adding depending on the plus or minus. For parallel connection, we could add conductivities, the opposite value for resistivity. And we could add current sources if they are present. Also, if here we have not voltage sources, but current sources that we could point like current J. If we have couple of parallel sources, we also could add them in parallel, the same as we did for voltage sources in series. It was our previous material. Then we practiced about equivalent transformation for different circles, and that was the final point. And also we say a couple of words about the main laws of electricity. If we know for which elements we are working with, if we know how to simplify these elements, we could use three main laws as Ohm law, which connects voltage, current, and resistivity. And in the most general cases, read like this. And also two Kirchhoff laws. Kirchhoff law about current, then total current in the node equals 0. And Kirchhoff law about voltage, that total voltage inside mesh also equals 0. These two laws are the conservation laws, a transformation of charge conservation law, and energy conservation law, just written in the form of electrical engineering. And that is quite useful, because all further mathematics, it will be just some complex transformation of these three main laws. Just mathematical transformations, and everything ground only on these three basic formulas. And speaking about mathematical model, just a general revision, how we build it and what assumption do we have, because it is the most important thing if we work on the computer, which assumptions do we make. First of all, we made assumption that we're working with direct current sources, then that our sources are constant independently on time or on load that we try to supply, just a constant value of current, constant value of voltage that is generated. Then our consumer, our resistance, also constant, independent on value of current, independent of value of voltage, independent of value of temperature, just constant thing. It is called linear electrical circles if we speak about constant resistivity. And also it is concentrated in one physical point. We neglect any spatial dimensions. We discuss if, for example, we have some equipment, some, for example, lamp that gives to us light. No, sorry for my drawing. I mean some electrical lamp. Or heating, or, for example, charging some battery, any consumption of electricity, or rotating some motor, any consumption. We neglect any spatial dimensions of this equipment and think that resistivity is concentrated in just one point. We draw like resistor, but mean that it is a physical point without dimension. And also the structure of our circle is stable. We didn't use any connections or disconnections of elements. We didn't change structure of circle. As we see it, it works long period of time in such stable form. This is our basic assumption, and it is called direct current linear electrical circles. Because such approximations determines our mathematics, and all this mathematics that we use, it is grounded on our assumptions. That is why I pay such attention about these basic points. Then, how this, and also the last thing about power, we also discussing that after we calculating current and voltages, the total power of all resistances equal the total power of all sources, or voltage source or current source, and it is called power balance equation. Here it is. And the total power of all sources should equals total power of consumer. Also, it is the transformation of energy conservation law. And for today, we will practice it a little bit further, how to deal with this thing on some examples here. And then we'll move to some mathematical transformation to simplify the number of equations. If we will see here, we have lots of equations to deal with, and there is a couple of ways to decrease the number of equations. It means move from the most direct method. The most general method is called just direct application of Kirchhoff law. We just taking these three laws and dealing with them. But transformation from this method, we could use couple others. It's called mesh analysis, it's called node analysis, it's called Thevenin theorem, and also we have superposition method. All these four other methods make for some part of tasks more simple mathematical calculation. Just the main idea to decrease the number of equations that we deal with. Let's see how it works. Let's start from the examples that we have here in our methodical book. and then we'll be moving forward. We have some mathematical model of an object of electrical network, and here we have 3 sources of voltage, E1, E2, and E3. And also here we have 2 consumers, 2 resistors, first and second, and applied voltage to open points, to open nodes. If we point them, for example, as point number 1 and point number 2, we have voltage between these 2 points. And we are asked what measurement of voltmeter will we have in this situation. We have 2 main measurement devices that called voltmeter and amperemeter. You could easily Google how they looks like. Just some measurement device for voltage. The main idea to measure voltage in volt, and the same as amperemeter. Measure current in network. There are lots of view how it's look like. Just the main idea, you connect this device and obtain the current in the circle. What's the difference between them? The main difference, how they are connecting and which type of resistivity do they have. Voltmeter is connected in parallel, and amperemeter is connected serial. That is why if you have some source of energy, for example, only one, and resistivity as a consumption. If you want to measure the voltage on this resistivity, you apply voltmeter in parallel to this resistivity. How it should work? The current that flow in this circle should stay the same, and this measurement device shouldn't influence on this current. That is mean when current reach the point of connection, all the current, almost 100% of current, should flow through the resistor and shouldn't flow through the voltmeter. Because if current will flow through the voltmeter, the voltage will decrease on the resistor, and the voltmeter will show smaller voltage that was before the connection. Because voltage equals current multiplied the resistance multiplied the current, it will be the voltage of measurement. And this value should stay the same. That is why to decrease the current through the voltmeter, to make it neglectable small, this voltmeter should have infinity high resistance. The resistance of this measurement device is very big. And that is why it is connected parallel. That completely opposite situation for amperemeter. Amperemeter should measure current. It connect serial. It is connected serial. And the current in this circle flow directly through the amperemeter. And this amperemeter also shouldn't decrease the value of current. The current without amperemeter and with amperemeter should be exactly the same. That is why the resistivity of this ampere meter should be neglectably small, almost zero. Not to change the value of resistivity, not to change the value of current inside this circle. That is important how we deal with it. If we have any voltmeter in the circle, we know that resistivity infinity high of this measurement device. If we have ampere meter inside this circle, the resistivity is infinitely small. It is mean that for this circle, that we have in our task, the equivalent scheme should be drawn like this. We have electromotive force as generator, resistivity, then other source of energy, E3, other source of energy, E2, R2, applied voltage, some applied voltage from the external source. And this voltmeter, if we are speaking about current, it does mean infinitely high value of resistivity, just open circle. And current will flow the central branch. Current will be absent here. Drawing like this. And if we are asked what voltage will be on the voltmeter, it means that we are asked what voltage will be between these points in central branch. How we could find it? We could apply the Kirchhoff law that we discussed previously. This law tells us that total voltage of sources should equal total voltage of consumers. Let's draw different colors to see the difference. The total voltage of consumers in general form. How many consumers do we have here? We have first consumer, first voltage, and second consumer, the second voltage. How many sources do we have? We have source number 1 in this mesh, inside this mesh. Source number 2, and external source that is given as voltage applied between points. 3 sources, 2 consumers. That is why we should write applied voltage from the bigger point to smaller one. If it applied between points A and B, it means that voltage is a potential difference. It is A minus B. And if it is positive according to initial data, the initial data is 40 volts. That means that phi A bigger than phi B on 40 volts. That is mean plus is here. Also, you see the direction of sources on this picture. That is mean they are all connected the same direction. It should be E1 plus E2 plus U equals 2 resistivities. Two resistivities. just according to this, voltage is also source and current are consumer. Current is the same because in central branch we don't have any current. That is mean only current will flow on the external mesh, and the value of current is the same through the all elements. All elements are connected in series. Then we could move this electromotive force in the right part of our equation because this is known variable, and write the equation in the form like here. And transform current to find current as only one unknown variable from this equation. I not exactly understand why these electromotive force are written in the right part, because in the left part it is more useful for us, and it will be in the left part from the starting from this equation. Just in some thoughts, author should write them here. Mathematically it's correct, but physically we will use them in the left part as I write before this, sorry. And the current will equal 3 voltages, divide on 2 resistivities, substitute all values from the initial data, obtain the current 4 ampere, flow from the plus to the minus in this direction, 4 amperes. And using this current, we could find the value of voltage between these 2 points. Because we could, if we want to find this voltage on the voltmeter, we could move or upper mesh or lower mesh for calculation. Both these paths will give us the same value. If we will go upper, upper mesh, we take source E3 plus applied voltage. They are directed the same in the same direction. You could see plus here and plus here. Also plus E2 plus source, and minus consumption of electricity through the resistor. The total voltage will be minus 10 volt. If we are moving from this point number 1, to this point number 2. The same if we are moving a lower mesh, it will be E3 plus consumption minus source, also equal minus 10 volts. How we could find the decreasing or increasing voltage, why we should add, why we should take with minus, how we could find the direction of voltage. Quite useful thing, it's called potential diagram. We could write the diagram how this voltage moves between points. Let it be point A, B, for example, C. Let it be D. There is no connection, that potential D also will be here. Then A, let it be E. And for example, F. All the potential we have. This point also will be A because no element between them. Then, if we want to draw the diagram how this potential will move through some mesh, we could start from, for example, I don't know, point D. Let our D will be 0. and point number D. And how the voltage will change through the mesh. The source will increase our voltage on the value of E2. Then it means after the source, point number C will be with voltage 20 volts, the value of source. 20. The potential E. Then through the current flow, in the direction of current, the voltage decrease. If you have some element, and current moves through this element, the value of voltage is a potential difference, and this element takes energy, and the value of voltage decrease. It means that potential at the beginning is higher than potential at the end. Consumption of electricity, and at the end, potential will decrease. That is mean that this value of C, sorry, I wrote E, it is C. The value of C will decrease on the value IR. IR, current I 4 amperes, resistivity R220, 4 multiply on 20, it will be 80. Then it means that this value C will decrease on 80 volts. It will be minus 60. Minus 60. I draw not exactly in the scale because I want to show the idea, and we don't have so much space on this drawing. That is why it is just for show the general idea how this voltage changes. It is point number B. Potential decrease. Then we have voltage drop from the A to B. That is mean that voltage decrease from A to B as a potential difference here. Then if we are moving the opposite direction of the voltage will increase on the value. The potential became bigger. Bigger on the value of voltage, it is 40 volts. It means minus 60 plus 40, it will be minus 20. Minus 20. And we moved to the point number A. Then what do we have? We have voltage source. And it increased the value of obtained voltage on the value of own number. It E3 equal 10, minus 20 plus 10 equals minus 10. And we came to point E, our last point. And if we see just step by step how our potential change from 0 to 20, then till minus 60, till minus 20, till minus 10 on the all of elements. If we will move on the other part of the circle, we will obtain just the same values. If we will move, for example, from point D to the source, this source on 60 volt decrease the potential because we're moving in the opposite direction of the source. We will move to this point. Point F will be the same potential as point B, as we see. No, just in the number, just because of the characteristic of elements. It will be other point, but with the same value. Minus 60, point F. Then current flows in this direction. It increase in the opposite direction of current. Increase the value of potential on the value of I multiply on R1. 4 multiply on 10 equals 40. We will move to the point minus 20. Point minus 20, it is point A, the same point A. We'll move here, and then the same source to the minus 10. For different ways, for different meshes, we obtain the same value as minus 10 volt of measurement of voltmeter. The difference will be in which point we connect plus, in which point we connect minus of this voltmeter. If we will connect plus to point number E and we'll measure minus will in point number D, move in this direction, we will obtain negative value minus 10 volt. If we will change the wires, connect minus and plus in opposite way, we'll obtain plus 10 volts of measurement. That is why if it is not so important for us the direction, in lots of situations, the measurements of voltmeter is taken by modulus, and we're just speaking about absolute value of 10 volts potential difference between couple of points. Okay, this is the application of Kirchhoff law for some circle, and couple words about measurements. Please, if you want to clarify something or discuss something in more detail, please welcome before we move to the next example. Generally, everything fine? The main idea is okay?
It's okay.
Okay, perfect. Then let's move further. Other example just to deal with measurement devices, ampere meter and voltmeter. What will be the difference between these two circles? The difference will be will current flow through the element or will not flow. As we discussed previously, the ampere meter has 0 ohm resistivity and voltmeter has infinity high ohm resistivity. Then in the first case, current in the first point will flow only through ampere meter because in the upper branch we have some resistivity, and this resistivity is much bigger than resistivity of ampere meter. The total resistivity of upper branch much higher than resistivity of ampermeter that equals 0. That is why current will flow on this direction. All current will flow through the ampermeter, and it will be the path for current. The second situation is completely different. Because our voltmeter with infinitely high resistance, the current won't flow through this voltmeter because R1 plus R2 is much less in resistivity than voltmeter, which goes to infinity, close to infinity high resistance. And that is why all current will flow in the external mesh, as you see here. On the external mesh. The difference will be in formula. Both this situation could be solved using the Ohm law. The current equals electromotive force divide on the resistivity, but in first case you have only one resistivity. In second case, you have all three resistivities. R1 plus R2 plus R3. In first case, you obtain value of current E divide on 20 as 5 amperes. In the second case, 100 over 100, as you see it here, it equals 1 ampere. And ampermeter will show you the value of 5 amperes. It will be its measurement. For the voltmeter, it could be found the same as in previous case. If you want to measure the voltage, you could go in this direction, bottom mesh, or upper mesh, using the Kirchhoff law for voltage. On the bottom mesh, it will be electromotive. Let's see the direction of current. The current direction will be here. Then it will be electromotive minus current. In the upper case, adding currents. In upper mesh, it will be I on R1 plus R2. It will be 1 multiply on 80. It will be 80 volts. In lower case, it will be electromotive force minus current and resistivity. 100 minus 20, 1 multiply on 20. It will be 80. Also 80 volts. That's generally how it's work, how we could obtain some measurements. Is everything fine? Is everything okay?
Yeah, it's okay.
Okay, perfect. Then I think let's see the last what it is here. Okay, let's see this one, and then some last practical task from methodical tutorial for problems solving. And we'll move to the next topic, to the transformation of mathematics that is called mesh current method. Here, about this task, what do we see? Determine the resistance and its power for this parameter of the circle. It is the reverse task, because in a straight task, we have value of source and resistivity, and is asking for current. For reverse task, you have or current or voltage, and you are asked about resistivity. Just to find the necessary parameters of circle to obtain the necessary working mode. For this task, if you have value of electromotive and current, that is mean that you exactly have and resistivity and power. Resistivity is only one inside this circle, and it could be calculated using the Kirchhoff law, connecting voltage, current, and resistivity inside closed mesh. It will be 5 ohms. And power, it could be found or at the point of consumer or at the point of source. At the point of source, it will equal electromotive on current. At the point of consumer, it equals I square on resistivity. Joule heating. Source gives you 10 on 2 equals 20 watts. For the consumer, Joule heating, square of 2 amperes current from the initial data, multiply on resistivity, also 20 watts. And it is the answer of this simple task. If you have couple, for example, of resistors, R1 and R2, in this case, it will be sum of these resistors, R1 plus R2. And in every formula where you have only one resistivity, you will obtain couple. And let's see some last example, and everything else, I think you will practice with teacher Ludmila on the practice. And let's see some solution, for example, 1.2, starting from the potentials. In this task, you have value of potentials from the measurements. It is circle number 1.3. Here it is. And you are asked to find all currents, determine all currents from this picture. What is interesting in this task, that you don't have the view of whole circle, because as you see, this current could be, let I draw them as green. This current could be connected to any other part of the circle. You works only with some part of general mesh, of general network, only some small parts. But if you have the necessary measurement of this part, you don't need the view of the whole circle. For example, because here could be some other elements, it could be quite wide circle with lots of elements, it could be 1000 elements, it doesn't matter. You are working only with some specific part. But if you have potentials in these points, it is enough to find all other values. You have resistivity, voltage sources, and potentials. How it is worked? Using the Ohm law in the general form. If you have potential of 0.1 and 2, the current could be found from the Ohm's formula. Potential difference plus value of source, it increase current, and divide on resistivity. The current in this branch, just through the one formula from the initial data, will be 2.6 amperes. Then you could apply the same formula on the current number 2, potential 3 minus 2 divide on the resistivity. From the initial data, it is 1.2 amperes. And the same with current number 3. Phi1 minus Phi3 plus electromotive over the resistivity, it will be minus 0.75 amperes. It is mean that the value of current will flow on the opposite direction. Everything is okay. If you obtain the negative value, it is normal. You just know that the real direction of current is opposite. But mathematically, it is the same that current on this direction, but with negative sign. And after that, you could apply the Kirchhoff law to find all other currents. If you see that green current and blue current concentrate in point number 2, their adding will give you current number 5, according to Kirchhoff current law. Current number 5 as sum, 2.6 plus 1.2, 3.8 amperes. Then the same you could use for current number 6. As you see, blue current minus red current will give you this pink current 6 as value minus 195. That is mean that real direction is opposite, but mathematically for this direction, it will be negative current. And the last one, current number 4, mathematically, it is first and third, both of them with negative sign, minus 1, minus 3, just because of direction, equals minus 1.85. Then this task is completely solved. You don't need to know what other part of system do you have. You just know that this current that flow to other part of system, other part of network, equals this value. Just like that. And you were applying here. I don't want to erase it, just one moment. I will return to the basic laws and then return to this task. You were applied here Kirchhoff current law from this formula in the points. And you were applying the Ohm law in general form inside the triangle. That's what you did. Okay. Before the next topic, maybe you want to ask something, maybe you want to discuss something.
No.
Okay, perfect. Just maybe sometimes it's look very simple because it is just basic ideas, and these ideas we will need for more complex tasks, for more complex mathematics. Just starting from them and moving forward. Okay. What we could say about methods for analyzing electrical circuits? Generally, we have two types of circles that we called simple and complex. Or in other words, more harder for solving. For simple circle, it's mean that we have only one source. For complex circle, we have more than two sources. Sources of electricity. What is the difference? If we have only one circle, then we could simplify all resistors near this source and solve our task without any system of equation. We don't need any systems, any matrices. We could just find total resistivity as we did last time and find current from only one source. If we have two sources, generally we cannot find such called total resistivity because total resistivity should be near source. But if we have couple of sources, the main question, near what source we should find this resistivity. That is why in complex sources, something we simplify that we could, but generally we cannot find total resistivity. That is why we use system of equation. In this case, we will have only one Ohm equation. For complex networks, we will have system of equation. Generally, it will be solved in matrix form. And dependent how many equations we have inside system, will be some mathematical approach to decrease the number. As less equation in system we have, it is better for our calculation. Our calculation became more simple. Then all mathematics will be applied just to decrease the number of equations. Let's see the difference. This practical task we don't need for now, till the next time. Let's see some task, for example, here. Okay, let's make it a little bit simpler. Okay, let's assume that we have such type of source, such type, sorry, of circle with two meshes, as you see. Two meshes, a couple of sources, couple of consumer, and we want to solve it. How it could be found? If we have only one source, if it would be simple circle. If it would be simple circle that we don't have other sources, we have only one source, circle like this. And I said that for simple circle, we always could find the equivalent resistivity, total resistivity of this circle. This resistivity should be near the point of our source. It is mean that we are searching for resistivity of whole network near the point of source. It would be our total resistivity. How it could be found? We are looking for serial and parallel connections from the previous lecture. We see that have serial connected R5 and R6, like here. Also, we have parallel connected R4 near these two resistivities. The formula for parallel connection looks like this. Multiplication in upper part and adding in lower part. And then we have serial resistivities connected to these parallel branches. It will be plus R3 and plus R2. It is total resistivity of whole network. Their total resistivity. Sorry, some technical moments. Okay, we are substituting resistivities here. The total resistivity for our circle. Then, after that, we could find the total current through the source. Let's name it I1 as electromotive force over the total resistivity. It will be here. After that, we could find other currents just in proportion which part of current will flow through R5 and R6 and which part of power will flow or part of current will flow through the resistivity number 4. The current as it is shown here, but I will change the direction, it will be more obvious. Current, let it be I4 and I6. I4 will be proportion to current I1, and I6 also will be proportion to current I1 on the, through the bigger resistivity will flow smaller current, through the smaller resistivity will flow bigger current. That is why this proportion will be reversed. It is called the method of opposite resistivity. We are taking the resistivity of opposite branch and see which percentage of current will flow here. If we want to find current I4 as a percentage of current I1, we should multiply on resistivity of opposite branch, of opposite parallel branch, R5 plus R6, and divide on the total resistivity, R4 plus R5 plus R6. For the current I6, the same reverse proportion, the opposite resistivity to find the percentage of this current of the total current I1. It will be R4 divide on R4 plus R5 plus R6. And as you see, if you will add I4 plus I6, you will obtain current I1. For example, if total resistivity, just to see some numerical example, if total resistivity of right branch equal, for example, 20 ohms, and total resistivity of central branch, for example, equals 10 ohms. And let's see that total current equals 3 amperes, let's assume. Then through the bigger current will flow, through the bigger, resistivity will flow smaller current. Through smaller resistivity will flow bigger current. What should we do? We multiply 3 amperes. If we want to find current here, we multiply 3 amperes on 20 and divide on 10 plus 20. It will be 2 amperes. For this branch, we multiply 3 amperes on the opposite resistivity 10, and it will be 1 ampere. As our resistors, which ratio do they have? 20 to 10. The reversed ratio you will get about current. 20 divided on 10, reversed ratio 1 divided on 2 from the total current. It is called the method of opposite resistivity, just to find percentage of current. And we see here that if we have only one source, we don't need anything else. We could find total resistivity and find all currents through this branch. Quite different situation will be if we have couple of sources. About this method on the current finding that we called opposite resistivity to find the percentage of current through the each branch. Is it okay? Is it clear, this current method?
Yes, it is.
Okay, okay, perfect. Yeah. Okay.
But I don't quite understand it.
Okay, let's, just in case I take picture of it, and let's show it in more simple way. First of all, some, how it could be said, some similar situation from different physics. For example, imagine the tank with water, some pool, some tank with water, pool with water. And if you have two pipes for water flow, the amount of water, okay, if they on the same height, here and here, yes, let's make normal picture, sorry. You have two pipes, one with small cross section, one with big cross section. You know that the amount of water will depend on the cross section. For the smaller cross section, the amount of water that will flow outside this tank will be smaller. In the bigger cross section, the amount of water through the same time will be bigger. And you could find the values of water, the volumes of water, just calculate what ratio will be between them, just to check the cross sections, just to compare the cross section. If you want to find volume of water flow from each of pipes, it will be just the opposite value of their cross sections. As bigger cross section, as smaller, as bigger cross section, as bigger volume you will get. As smaller cross section, as smaller volume you will get. Then the same situation is for resistors. If you have the same idea, if you have two parallel resistivities, and the total current that it inflow to these resistivities, how to find in which percent will flow on the one resistor and which percent flow to the second resistor. How to find how this current will divide on resistivities. It could be compared using conductivity. If it is current number 2 and current number 1, as cross-section of water pipe tells us how simple water will flow through the pipe, then conductivity tells us how simple current will flow through the object. The ratio of these currents will equal the ratio of conductivities that is pointed as G, conductivity in Siemens, how simple current will flow, between these two resistors. And conductivity, it is opposite value for resistivity, because resistivity tells us how hard for current will be flow through this object. And if we transform this ratio, we will obtain the opposite proportion. I will write it a little bit here. We obtain that I1 divided on I2 will equal R2 divided on R1. Then, for example, if you have resistivity of 10 ohm, R1 equal 10, and resistivity 20 ohm, and total current equals 3 amperes. How these 3 amperes will divide between two resistors? In the ratio, how their resistivities ratio between each other. Then, if resistivity is 20 per 10, then current will divide as 1 per 2, just the reverse proportion. 1 ampere will flow on the bigger resistivity, 2 amperes will flow on the smaller resistivity. How we find that 3 will divide as 2 per 1? Just using this resistivity. In first case, we take 20, divide on 20 plus 10. In the second case, we are taking 10 and divide it on the same value, 10 plus 20. It gives us this ratio. It is just a proportion and called the reverse resistivity law or rule, how to find the value of current. Just situation could be found as water flow through some pipes of different cross-section. Something like that.
Okay, understand. Thanks.
Okay, welcome. Thank you for question. I think it will useful for other guys that will look at this video just at home, who are not present today. Okay, and then the last for today, I want to discuss the situation of couple of sources, because if we have situation like this with 3 sources, we cannot find the total resistivity. The idea of solution of previous task, the idea of solution simple circle, that we are finding current as electromotive force divided on total resistivity. And this total resistivity was found near the source. But here we have 3 sources. Near first source, we have 1 resistivity. Near second source, we have completely other resistivity. Near the last source, we have also completely other resistivity. That is why, which resistivity should we take? In complex network, we cannot find just total resistivity because we don't know near what source we should find it. This value could differ. That is why we are using other methods, generally specified for complex networks. Using laws, we are using just Kirchhoff laws. Kirchhoff laws and make an equation. Our idea using these laws to find system of equations and solve it. System of equation and solve it. How we should write this system? For complex network, how this system should be found. We are writing the Kirchhoff law in the first circle, Kirchhoff law on the second circle, and Kirchhoff law in the point of current connection on the node. In the first circle, in the first mesh, we could write that electromotive force number 2 minus electromotive force number 4, these two sources. The current will equal consumers. That, how many currents do we have here? We have first current left, second current central, and last current right. Then we have this current, let it called I2, on the value of resistivities. Let it be, for example, R2. R2 plus, also R2, let it be then, for example, R1. I don't see R1 here, let it be R1. R2 plus R1. And minus, because of opposite direction, as you see on the current, I4 in the opposite direction as we see, as we look on the direction of mesh. It should be minus R4 on R4. Then for the next mesh, we have also two sources, E4 positive, E6 negative. And their difference equal current. I4 the same directed for the second mesh. It will be I4 with plus on R4, but with minus for the last current because of direction. The arrows are opposite directed. Minus I6 on R6, and let it be, for example, R5. Plus R5. And the last equation tells us about current in this point. I2 plus I4 and plus I6 in total equals 0. It is system of three equations. Electromotive forces is known for us. Resistivity also is given. And unknown variables, I2, one unknown variable, I4, second unknown variable, and I6, the last one that should be found. Then I2, I4, and I6 should be found 3 unknown variables from the system of equation. And it is solution. We are making matrix from this equation and finding the value of currents. The task will be solved. We'll practice about this next time, just not to make a lot of information is in one lecture. But the main idea is like here. For simple circle, you don't need the system of equation, because for simple circle, with only one source, you could find the total resistivity. But for complex source, for complex network, for complex circle, you have to make a system. And from this system, you will get currents. From simple circle, you will get current from the total resistivity. That is the main difference. And all what we will speak further, it will be how we could make the system in the simplest way, such called Kirchhoff application method, such called mesh current method, such called node voltage method, or superposition theorem, or Thevenin theorem. All these methods, they will be just about how to decrease the number of equations. For example, not 2 equations, but 1 equation. You will see that if we will, for this circle, if we will use a mesh current method, instead of 3 equations, you will get only 2 with the same answer. For example, for node voltage method, for the same circle, you will get only 1 equation. It will be the simplest way of solution. But the main idea is here. For today, I think about material, that's all. If you want to ask something, please welcome. If this idea is clear, then perfect. Is everything okay?
Clear. Yeah.
Okay. Then perfect. Then wish you good luck. Just one moment. Okay, then just wish you good luck, wish you a nice day, and see you on the next Friday at the same time.
Thank you so
Okay.
much. Have a lovely
Thanks.
weekend. Take
Have a
care.
nice day.
Yeah.
Goodbye.
Thank you. Goodbye. Bye.